Good morning or afternoon, wherever you may be. My name is Andy Deal. I'm your host. Welcome to our webcast today, focusing on working with composites. We have Michael Allegro and Greg Borgerson, two solutions consultants from Saratech. Um, Before I pass the presentation over to Michael and Greg, I'd just like to remind everyone that if you have any questions at all, please go ahead and type it into the chat box and we'll get to them in the Q&A portion. And also, after you log off the webcast today, there's a short 5-question survey that pops up. Please just take a couple minutes to fill that out. That will help us a lot in future webcasts. With that, I now pass the presentation over to Mr. Allegro and Greg Borgerson.
Like Andy said, good morning or good afternoon, everyone. We appreciate you attending this webinar. My name is Michael Allegro. I'm an enterprise sales executive with Saratech. I have about 30 years experience in the CAD/CAM CAE industry, and I'll tell you what, I am very excited about tools, some of the advanced engineering technologies that we're going to talk about today, specifically for composite design. I remember seeing back in the early 90s at Northrop, they were just getting into the development of the use of composites, and now I have a customer today who's developing a launch vehicle that the structure of that vehicle is nearly 90% composite laminate layup. So it's really exciting to see where the industry has gone and the use of composites is being used. And I look forward to talking to you guys later in the presentation about some of the challenges that companies face regarding the design of composites and maybe some of the solutions that we have that can help reduce some of those challenges. Greg?
Hi. Hi. My name's Greg Borgerson. I'm a solutions consultant with Saratech. I'm located in Northern California and have over 20 years of software experience. Today, with the growing need to make products lighter without reducing strength, working with composites have become very popular. Today we'll discuss some of the challenges other companies have seen and solutions on what have worked for those companies. First, I'd like to tell you a little bit about who Saratech is. Saratech has been in business for about 14 years. We focus on optimizing your engineering investments. As an industry leader in the PLM space, we are Siemens' top channel partner in the U.S., and we work with other software platforms as well. We're headquartered in Southern California with a presence in 8 different states. Carbon composites are extremely versatile, and therefore the optimal property required for almost any application can be developed. Performance demands for the same strength, carbon composites are 80% lighter than steel and 60% lighter than aluminum. Carbon composites exhibit higher stiffness to weight ratios than your conventional materials. Weight reduction is in demand in a number of industries, from commercial airlines, fighters, marine, and automobiles. Dimensional stability can be tailored to match surrounding structures, thereby minimizing thermal stress. This is extremely important in aero engines, high-performance antennas, scanning, and imaging equipment. Another great benefit is lower assembly costs for aerospace and defense, along with high-volume automotive applications. Carbon composites are essentially inert even in corrosive environments. The properties of carbon fiber composite structures depend on the selection of the components and how they are arranged. The 2 principal elements of carbon composite structures are the matrix and the fibers. The selection of the fiber, its orientation, and its layup order play a dominant role in determining the characteristics of the finished structure. The matrix serves to keep the fiber in the desired position. In addition, the matrix imparts important properties to the composite structure. The challenge is that, unlike working with metals, that you're designing the material at the same time you're designing the part. In addition, there's a coupling of the part shape and the manufacturing process selections that are tightly coupled to the materials. This adds another level of complexity. Composite part design is a true concurrent engineering process requiring collaborative between different departments, design, analysis, and manufacturing. While it's possible to develop a composite part without the use of engineering technology that support a concurrent engineering process, the results are typically less than perfect and do not achieve the weight savings, cost savings, production rates, and product quality that is desired. In fact, the end result is a lack of experience. The use of traditional design approach and the lack of vision of the complete picture, this leads to composite parts and products that are frequently over-designed. Engineering technology is key to addressing this and designing a product that capitalizes on the full benefit of composite materials. Some industry statistics show that without the correct technologies in place to support an integrated and holistic development approach, results are often poor. Here are just a few of those statistics based on 140 respondents from different composite intensive industries. What you'll see is most companies either replace a metal part or consolidate just a small number of parts. Very few meet their weight targets due to over-design. Many saw the parts increase the cost, and without the right collaborative process and engineering technologies in place, it is very easy to slip schedules. If you take everything from design cycle efficiency to reusing laminate data versus or compare single-purpose laminate data to good throughput and product quality compared to slow and inconsistent manufacturing processes, are normally the results when organizations invest in its people and the right technology.
So this is Michael again. I'm going to kind of take you through some of the design considerations that go into composite designs and kind of look at the life cycle of composite design so that we can identify some of the challenges that exist currently without advanced engineering technologies, and then how advanced engineering technologies can address some of those challenges. So the starting point of a composite design, whether it's done the traditional way or with the full benefits of engineering technologies, no matter what, the feasibility studies need to be performed in the allotted design space that's required, but there needs to be a geometric starting point for the analysis. So full feasibility studies, whether it's done with just the load conditions of a, which is the traditional method, is just generally with load conditions. Advanced technologies can allow the ability for the use of looking at manufacturing processes, different geometries and different materials that can be the benefit of an integrated CAD and CAE environment. So, generally there's the starting point of the surface, or the part geometry. But once that concept has been selected after the feasibility studies, there are still many challenges that the process faces when there's that design exchange and communication between the designers and the analysts regarding the composite data. And one of the main obstacles there is just generally the language in which these two disciplines speak. So, for example, a designer might speak in terms of outside mold surface, but The analyst speaks in terms of, mid-surface, which are used for, meshing and so forth. So the designer and the engineer, and the analyst, I'm sorry, need to be able to exchange this information frequently. But traditional methods of exchanging, interpreting, and converting this information can be extremely time-consuming and can also be very error-prone. So engineering technologies allow provide for the interoperability between the CAD and CAE applications so that they can share some of this composite design data, and they can perform many iterations in a shorter period of time. Also, because of that automated interoperability of the data, it's more efficient and there's less risk for error. So a traditional approach to composite design has been, spreadsheets or solid layers of material in a CAD system. But both of these approaches, don't take advantage of the downstream information like material behavior and the effects of manufacturing, and leave those decisions to be made much further down in the process, oftentimes at the production point, where if changes and decisions are being made there, cost companies a lot more time, money. They affect the production rate and they affect the quality of the part, and they never really do take advantage of the benefits of composites. So engineering technologies can allow you to design in your CAD system using design methodologies that are specific to your industry, but not only that, but allow you to examine and sample design methodologies with the geometries and the different variables so that you can explore what the best possible design method might be for your organization and your parts. So essentially a laminate is made up of a stack of plies. So although it might be feasible to manage simple composite parts in traditional manners, once those number of plies get up into the tens and hundreds, it becomes almost impossible to do that. So engineering technologies can allow the design and communication of composite parts, incorporating specifications and requirements directly into the part to drive the development of the part. So laminate family tables, otherwise known as laminate specifications, are predefined stack-ups that adhere to a particular set of rules, and then those laminate specifications are applied to particular regions of a part. So engineering technologies typically reuse and consume the specifications that are defined by the analyst and allow you to apply those to different regions of the part based on their analysis and their input into the specification. So the opportunity there is that it eliminates the manual rebuilding of these family tables, which can introduce human error and cause a lot of rework downstream. So, drop-offs are a particular part of the composite design process, and drop-offs are used to accommodate different geometries that might be adjoined to the composite, or in areas where there might be some relief that's required. But what happens in these drop-off areas is that the amount of stress increases in the laminate at that area. So there's different types of drop-offs. Here's 3 examples. One's called linear descending, one linear ascending, and then a custom diamond-shaped one. So because there's this additional stress in these areas, the shapes, these transition areas need to be managed and analyzed accurately. But then they also need to be designed accurately. So there's 2 considerations that need to go into these particular drop-offs. One is certainly the number of plies being dropped off, but secondly is the stagger distance, or the rate at which the plies are dropped off. So it's really not feasible for a designer to carry out a detailed analysis of the entire structure, especially with these drop-offs existing throughout the structure, without the use of engineering technologies that can capture and reuse this information as company specifications. Not only do these does this aid the designer in developing the part itself, but it provides a meaningful way to communicate with the manufacturing floor downstream. Another design consideration is ply corner behavior. So here's just an example. Chamfering is sometimes used where drop-offs just don't make sense, and specifically when automated fiber placement is being used. So once again, this is an area where engineering technologies can be used to capture these considerations as standards and minimize the amount of effort that goes into design, as well as reduce the number of errors downstream. So automated fiber placement can be fantastic for large panels, and can ensure faster and more consistent layup. However, once again, design considerations must address certain design considerations. I'm sorry, certain challenges that are faced based on, for example, using automated deposition or automated layup. There's the effect of minimum course length, which results from the machine that's laying out the material. It's where it's pinching and rolling on the material and the cutting head itself. So whether chamfers are being used or flags, like this example in the lower right-hand side, which is called a bird beak, these decisions really shouldn't be left up to manufacturing to make, because these decisions can affect the overall design of the part. So using engineering technologies, once again, allows you to capture these considerations as specifications, and kind of begin to develop a company standard based on the type of parts you're developing in-house. But alternatively to automated fiber placement, manual layup of composites is still probably the most popular usage of composite material and used by most companies out there in industry. So with manual layup, splicing and darting are important design aspects, and if left up to manufacturing, three undesirable outcomes can occur. First is that the splice or the dart of a particular orientation of plies is repeated in the same location. The second is that the splice or dart is applied inappropriately and in a critical area where a particular type of splice or dart should have been used. And third, because of these darts or splices not being defined up front, there's a lot of trial and error within that process, and there's a lot of wasted material that's the result of that. So using engineering technologies can ensure that there's communication of these repeat patterns, that critical regions are identified, and that there is appropriate use of splices and darts in those regions. And also that the splices and darts are used to develop ply templates that can produce a more repeatable and predictable manufacturing process. Design and iteration, or design and analysis iterations, they must be performed to eliminate the over-design of composite parts that is very common that takes place. So this is where a concurrent engineering process is used to couple the part shape, the material, and the manufacturing processes to achieve the best product solution. The performance of composites is very dependent on the fiber orientations in respect to its loading, and it has been shown that fiber misalignment has a significant impact on the modulus and strength of a composite part. For example, some studies have shown that misalignment of fibers by as little as 10 degrees within a, just between two ply specimens can cause a loss of strength of nearly 40%. So the analysis folks usually, begin with an idealized fiber orientations and really don't take into account the material type and form or the effects of manufacturing process or the part shape during the layup process. Ignoring these factors means that material break or knockdown is used and highly conservative safety factors are used, which results in over-designed parts. So how do we eliminate some of these challenges of over-designing composite parts? Well, the inputs into the iterative process really need to be understood, and then the outputs from that process can result in better parts. One of the most important parts of the design process is the iteration that occurs between analysis and design, but in coordination with the physical test data that comes out of manufacturing. However, companies like yourselves are being squeezed and pressured to have to do these virtual designs and builds requiring engineering technologies that can exchange this critical data about the laminate being developed. So in an effective iterative process, the analyst needs to be able to exchange the laminate specifications that he's developed from the CAE application and exchange those with the design engineer using CAD. And subsequently, the design engineer needs to be able to communicate the detailed laminate that he's developed in CAD to production solutions that support things like nesting, laser assisted layup, path planning, etc. And the design engineer needs to be able to simulate and predict the fiber orientation based on the manufacturing process that's being used and exchange them back with the analyst for performance validation. But in addition to all of that, the manufacturing engineer needs to be able to communicate the resultant fiber orientation from things like path planning and inspection that are achieved based on the mold or form itself and the machine and other material limitations that he's discovering down on the shop floor, so that the design engineer can then correlate that back with what he's used for his predictive fiber orientations. So I've only kind of touched on some of the design aspects and design considerations that go into composite part design. So you can see, based on the number of inputs that, composite design can be much more complex than traditional metal part design and manufacturing. And there are engineering technologies that exist that can support this, entire design process. There are analysis technologies such as NX-CAE, which includes linear and nonlinear analysis for composites, and then also specialized tool sets for, laminate optimization that provide the basis for this whole development and iterative process. And in combination with an open format, excuse me, that allows you to exchange this this information, that's used by Siemens and other leading composite CAE solutions, this data ends up being reusable. In CAD, the part of the upfront process, in combination with specialized engineering solutions for composites like FiberSim, it can support the initial geometry creation and then take some of these industry-specific driven design methods to minimize the manual geometry creation and then also be able to assist in all the changes that take place, throughout this iterative process. FiberSim can assess the manufacturing producibility and predict fiber orientations. That is, so important to optimal use of composite materials, and that can be exchanged, excuse me, with the analyst using the same, open format, so that it ensures that this iterative cycle is possible and that the parts are optimized as the best they possibly can. And then FiberSim can also create the manufacturing output data sets so that they are in a repeatable format, in a common language that the manufacturing floor understands and continues to see. And this provides, better predictive manufacturing producibility, as well as more consistent manufacturing downstream. Excuse me. So what can we expect out of engineering technology? Well, first there is the digital authoring of the composite designs, reducing the complexity, but also looking at the variables that are really the benefits of the composite materials. There's the ability to ensure that specifications and requirements are met, but actually driving the design from these specifications themselves versus trying to apply them in a CAD space without the use of these engineering technologies. Then there is the accurate prediction of material behavior, and being able to look at different options for materials and manufacturing processes, and then defining the processes in conjunction with the manufacturing engineer. So FiberSim has been able to do this for a while and address these issues for some time, but with FiberSim being a best-in-class engineering technology, it addresses some of the additional benefits of data management and the reuse of specifications, requirements, standards and processes into a single interface that includes CAD and in some cases CAE. For example, with Siemens NX, the FiberSim is built right into the same CAD and CAE environment that engineers and analysts have been using for years. It can address the interoperability between disciplines, like what was mentioned earlier, the analyst exchanging his laminate specifications with the design engineer communicating detailed laminates information from CAD down to the production solutions to support nesting and laser-assisted layup and so forth. And finally, FiberSim is available for multiple CAD packages to support today's global manufacturers. So FiberSim, as I discussed earlier, FiberSim allows companies to design composite parts in whichever design methodology makes sense for the particular industry that they're in, or based on the type of part they're designing and manufacturing. You've got different design methodologies built right into FiberSim to help you address some of those issues. It's available in multiple CAD solutions, Siemens NX, CATIA V5, and PTC Creo. It does provide the interoperability with CAE applications, unidirectionally or bidirectionally. It supports multiple output formats. So some companies just need to work with flat patterns. Others are doing laser projection. Some need to be able to share the information with other suppliers or OEMs, and you can do that with the composite step format, plus all the documentation output options that are available for downstream manufacturing operations. And then there are some specific industry applications that are available right within FiberSim. Excuse me. So what I wanted to do was just take you through a quick couple of snapshots of FiberSim. So here's a screenshot showing the ply layup of one particular laminate. Here you can see the orientation specified with the angles there. You can see which rosette is being used for the starting point of the composite layup. But then if you look further down along the interface on the left-hand side there, you can see all the other areas in which FiberSim can capture and reuse information so that you can begin to standardize and make your design and manufacturing processes for composites more repeatable. So what I did here is just kind of bringing you back to that slide where I showed the laminate family table and the laminate specification, where the colors you can have a more visual view of the laminate orientations based on color. Here's one example of a dart for this particular laminate ply layer. You can see the dart there in the lower left-hand corner, and that eliminated some wrinkling and buckling, and buckling on this particular part at that region. And then you can see the corresponding flat pattern that results from that automated analysis of the dart at that ply. And here is a screenshot of the drop-off profile and a corresponding cross-section view of that. So you can see down at the bottom the drop-off pattern options. You've got the two most common ones, and then the ability to create a custom drop-off for any particular region. And then you can see higher up in the dialog there where it says corner type, you've got the different options for how to handle corners and so forth. So to summarize, there are many benefits to composite materials. Mainly that is the strength to weight ratio that exists with composites, and that the challenges of composites design, because of its multiple input variables, generally result in over-designed parts that really don't meet the cost, schedule, and weight targets that companies are trying to achieve. But FiberSim is a multi-CAD composite design and simulation solution that can greatly reduce the mistakes made by many organizations adopting or perfecting their composite part manufacturing initiatives, and begin to address those challenges that companies are facing with their composite design process. So I just wanted to thank everyone for your participation in the webinar. Hopefully you got some valuable information out of this. Certainly if you want to follow up with us, we have some contact information here, and we'd be happy to answer any questions, take a deeper dive into FiberSim or any of the other Siemens product solutions. And I think I'm going to hand it back over to Andy to address any questions that might have come up.
Great. Thank you, Michael. Thanks, Greg, for your presentation. Obviously, in 30 minutes, there's only so much that we can share with you. Like Michael mentioned, if any of you want to see a deep dive and a more specific presentation that is, more applicable to your organization and your process, please make sure to contact us, and we'll be more than happy to help you. At this point, I know we're 5 minutes over our allotted time, and we didn't have any questions that came in during the presentation. So I'm going to respect everyone's time and end today's webcast. But I do want to remind everyone that when you log off, please just take a couple minutes to fill out our survey. It's only 5 simple questions, and it will really help us out. Thanks for joining us today, and looking forward to see you all on a future webcast. Thanks, Michael. Thanks, Greg.